This is the Sound Waves Lab. The objective of this lab is to measure the speed of sound in the lab in two different ways. One using an open pipe, a pipe that's open at both ends, and one using a half-closed pipe that's closed at one end and open at the other. If you get two good readings for the speed of sound, and if you take accurate measurements, then that's enough to get you a good mark in this lab. When you first come to the lab, it will probably look something like this. The microphone will still be in there on its rod, and the piston will still be in at one end. So the first thing you need to do to start the lab is to get rid of them, because you're going to be starting with an open-ended pipe, doubly open-ended pipe. First thing to do is to place the microphone directly into the hole beneath the speaker. The lab manual doesn't say to do that, but that's what you should do. That will give you the best results. Also, the lab manual doesn't tell you, but what you should do if you want to get good results is actually place the tube all the way up to the end, like that, so there's no gap. There's no gap between this perspex and the tube. The reason for that is when there's a gap, then the sound coming from the speaker is not as loud, and it means that the signal to noise ratio, the noise coming from the lab, is not as good. This maximizes the signal to noise ratio, which means that lab noises have less effect, and actually you will get a stronger signal in the oscilloscope. Also, make sure that the little preamplifier attached to the microphone is switched on. In other words, that you can see the red bit there. At the end of the lab, please switch this off, because there's a battery inside and it keeps running out. So at the end of the lab, make sure you switch it off like that. During the lab, make sure it's on so that you actually get a signal from the microphone. This is the sound wave generator you'll be using. When you're actually putting a signal through, turn this knob as far to the right as possible to the 25 setting to make the sound as loud as possible. Also, this top one, make sure it's on maximum. It's not what the book lab manual says, but if you have a louder signal, you have less error. The scale of the frequency that you'll be putting through, at the moment this is set to 100 Hz to 1000 Hz. If you do that, that's 1000 Hz to 10 kHz, and you change it by turning this. Never believe the dial reading that you get here. That's just an approximation. You should determine the precise frequency using the oscilloscope. First thing, make sure that all the red knobs are turned as far as possible clockwise. Next, you want two signals on the screen at the same time. To get that, you have to choose the right amplitude on the screen. The amplitude is volts per division. That's these knobs here. This changes the amplitude. So this makes the waveform more sort of on the screen more pronounced. You have to press the Alt button, ALT there. Make sure that the source is channel 1, and make sure you haven't grounded anything. Make sure this is this here is not on ground. Well, if that goes on ground, that's what happens. Sweep time per division. One division is one big square. When you're reading off the screen, make sure you are directly in front of the screen, because there's a distance between the lines, the grid lines, and the signal. If you're off center, you get parallax error. Parallax error is the error you get from two slightly different viewpoints. You have to be directly perpendicular to the screen when you read it. Sweep time per division controls the wavelength that you see on the screen. There, I've set the sweep time per division to 0.1 milliseconds. That means one big square represents 0.1 milliseconds. So, if I want to measure the frequency of this signal, I check very carefully how many wavelengths there are there. There's one, what did I say? 1, 2, 3, 4, sorry, 4 divisions per wavelength. 4 divisions, a little bit more than 4. Little tick marks are 1, 2, there are 5 of them. So this is 4.2, 4.4, 4.6, 4.8, 5. So that's less than 4.1, so maybe 4.05. 4.05 there. So that's 4.05 divisions at 0.1 milliseconds per division, and that tells you the period, and the period is 1 over the frequency. Don't forget that milliseconds is 10 to the minus 3 seconds. Now the pipe here has an open end at the far end, and at this end, well, there's a speaker there, here, but that speaker is forcing the air next to it to move like a sine wave. So there are antinodes at that speaker. So that is effectively an open end too. But it's a forced vibration. It's a forced oscillation. But still, you can consider the pipe to be doubly open, at least to an approximation. Notice the tube is closed here and the microphone is snugly in the hole under the speaker. That works well. Start off at 1 kilohertz and work upwards. Go upwards, and you have to find resonant frequencies. Now let's have a look at the oscilloscope. I've set it at 1 kilohertz, and I want to set the screen. Hang on. Okay. You don't really need the reference signal at the moment, but I want to just set the height, the amplitude, using the volts per division dial here, volts per division dial. I want to set the height so that when I come to a resonant frequency, here we go, increasing the frequency, increasing. There it goes. There's a resonance in the tube. We don't know which resonance it is. We don't know if it's a second, third, 10th or 15th one. We don't know yet. But there it is. Let's measure, let's find the position of the, let's find the frequency accurately. So to do that, I'm just going to make the peaks quite pronounced. Here we go. And I'm going to change the frequency slightly. There. That's spot on the resonance. I'll shift the wave across using this dial here, position horizontal. And I'll make sure I'm looking at it from directly on, like that. And I'll count the number of divisions. 1, 2, 3, 4. Between 4.4 and 4.6. It looks about 4.5, a bit more than 4.5. Let's focus it. Doesn't make much difference. I'd say 4.5, 4.55 divisions. 4.55 divisions, sweep time per division, .2 milliseconds. So one of his big divisions is 0.2 milliseconds. So that's 4.55 times 0.2 times 10 to the minus 3 seconds is the period. 1 over that is a frequency. Write down all the data, divisions, time per division, period, frequency, and then you find the next resonance. Let's have a look. Increasing in frequency again to the next resonance. There you go, there it is. Again, let's find it carefully. There. Shift it across to a convenient position. And now we've got 1, 2, 3, 3.2, 4, 6, 8, 3.8, between 3.8 and 4 divisions, maybe 3.9 divisions, that one, 3.9 divisions, and a sweep rate, sweep time per division, the same as before, 0.2 times 10 to the minus 3 seconds. So you work out the period, and then the frequency, and also you find the difference between this frequency and the previous one. You do that maybe 5, 1, 2, 3, 4, 5, 6 more times, going up in frequency, or you might do it 3 more times going up in frequency, and then you go back to 1000 Hertz and go down in frequency. See what happens. And then the lab manual says, by considering the differences between the resonant frequencies, construct a linear equation describing the resonant frequencies. Well, what all that means is, suppose you get an average difference of, I don't know, for argument's sake, 200 Hertz, or say, 200 Hertz, just for argument's sake. Then if this is 1100 Hertz, take away 200, that's 900, 700, 500, 300, 100. So your linear equation is n times delta f, which is 200, plus 100. That's if you want to do that. I get my students not to do that, but to do something a little bit different. And I'll explain what that is now. at this point, I think a fun thing to do is to actually find the speed of sound in the lab. And the way I'd do that is to use the results you've just got to find the speed of sound. But you need to derive an equation first, and I would just start you off without actually giving you the answer. So let me just start you off by reminding you of some high school physics. Resonance in an open pipe. So in an open pipe, the fundamental occurs when the length of the pipe equals a half a wavelength. And you see there's one node. This represents the displacement of the particles in the longitudinal wave. At the ends, the displacement is maximum. In the middle, there's a point of zero displacement, a node. Antinodes, and node. The next resonant wavelength has two nodes, and L is 3 lambda on 2. Next, L equals 5 lambda on 2, etc. And in general, the length, the resonant wavelengths, the nth resonant wavelength is given by, so I actually should put a subscript n on that, L equals n lambda on 2. Well, let's believe that, let's take for granted that the product of the frequency and the wavelength is the speed of sound. Now that's not quite the aim of, that's not quite what this experiment is about, but as I said, I'm actually modifying the experiment to make it what I think is more interesting. So I would like students to measure the speed of sound using an open pipe and also a half open pipe. So using C equals F lambda, you substitute into there and you get that the length at resonance is n on 2 times C on Fn, where n is the nth. The Fn is the nth resonant frequency, and so let's just zoom in on that, make it easier to see. And so just rearrange. Fn is n on 2 C on L. So this is the basic equation for the nth resonant frequency in an open pipe. And what I would like you to do is to find an equation for delta F. Okay, oops, delta F, that's meant to be a delta, sorry about that. That's a delta. Delta F, and what's delta F? Delta F is just the nth resonant frequency, take away the n minus 1th resonant frequency. So delta F, remember, is something that you've measured experimentally. And so you know that number, and this difference will only involve C, 2, and L. All of these, L is known, 2 is a number, C is what you're looking for. So find out what that is in terms of C on 2L. There's going to be something times C on 2L. Find out what it is, and now you know delta F, so that will tell you, that will give you an equation for C. I'm not going to tell you what it is. This is something that you should find. So this will give you the speed of sound that you measured in the lab using the open tube. You'll use exactly the same procedure for the half-closed tube, except of course these diagrams will be different and this will be slightly different. For the half-closed tube part of the experiment, you can't just close the tube off by inserting the piston and putting it to 60 centimeters, because this piston becomes part of the resonant circuit, part of the resonant equipment, and and it changes the resonant frequencies. It actually becomes part of the system and interferes with the system. It changes the system. So you need to prevent that using the Chuck's super wipe trick. Chuck's super wipe trick is, there's the Chuck's. You gotta wrap the Chuck's like that into a nice sort of rectangular shape. Here we go. I'm wrapping it around like that. Wrapping it around, wrapping it around. Okay, and I'm putting it in like that. Use a ruler to stuff it in properly. And let's see if I can find a ruler. I can use the rod. Just use the rod to stuff it in properly. So you place the piston at the 60 centimeter mark. Sorry about that. On the 60 centimeter mark. There, you just hold on to it, hold on to the piston. Oops. There, and just stuff the Chuck Super Wipe snugly against it to prevent the piston vibrating. And it moves along a bit, so you just move it back. This end, you just attach on as you normally do, like that, like that, and now this is ready to go. Now the half closed tube is ready to go. As I was moving that tube, if I look at the microphone end, let's just move the camera along. There's a gap has opened up here. Whenever you touch the tube, this tube tends to slide and a gap opens up here. Just try to keep this gap shut all the time to maximize the amount of sound coming in there, minimize the amount of noise from the lab going in there. Contrary to what the lab manual tells you to do, start at about 1000 Hertz and work upwards. Find the first resonant frequency above 1000. It should be around 1200 somewhere, a bit below, a bit above, I can't remember. Measure that frequency, then the next one, measure that frequency off the oscilloscope, and the next one, and the next one. Find the differences in frequency, and then repeat the analysis that you did for the double open tube, this time using the half closed tube, and find the speed of sound using your from your measurements. So let me start you off with the analysis. This time we've got a half closed tube, and the fundamental looks like the fundamental looks like that. Where again, this is we're looking at the displacement of the particles. As they move longitudinally. So L, that's L. L equals lambda on 4. Down and up and down. So that's one node, that's two nodes. L equals 3 lambda on 4. And the next one, you know, just from high school, L equals 5 lambda on 4. And in general, you've got an odd number multiplying lambda on 4. So you need what I want to do is to write this in a general form, indexing each successive one with an n going from 0, 1 to 3. So how do you generate an odd number? An odd number is 2n plus 1 lambda on 4, and as before, that's a subscript n. Again, let's just believe that the product of the frequency and the wavelength is the speed of sound. Then L equals 2n plus 1 C on 4f, f subscript n. So we've got f subscript n is 2n plus 1 C on 4L. That's our basic equation for the FNs, the nth resonant frequency for a half closed tube. And now what I want you to do is, if your demonstrator allows you to use this this method, and hopefully they will. See, delta F is something that you measured experimentally, and delta F just is defined as Fn, take Fn minus 1. So you need to substitute n minus, you put in the equation for Fn, and then you put in the equation for Fn minus 1 here, and you subtract the 2. And that will give you an expression in terms of C and L, something here in terms of C and L. I'm not going to tell you what it is, you can find it for yourself. And so you're going to find C is some expression here in terms of delta F, some expression here which has delta F in it, C in it, and L in it. And, oh sorry, not C, just delta F and L in it. This is a number that you measured, and this is a number that you can just, well, you know it's 60 centimeters. It's actually a little bit more than 60 centimeters, so check it carefully. Anyway, you can find the speed of sound using this. How close do you get to the previous value that you got? That's all I want to say about the Standing Waves Lab. If anyone has any questions, you can post it up on the WebCT discussion board, and somebody will answer it soon enough.